Okay, what is up guys, and I'm Sikesh, and today I'm going to be teaching you something rather quite simple. So, the question as you read it is find the volume of the solid generated by revolving the region bound by y is equal to square root x, y equals 1 from the line x equals 1 and x equals 4. About the line y equals 1. So, there's a lot of words there, and it might get confusing at the start, but we need to break this down step by step. And the best way to, actually do any of these problems is by actually drawing a diagram. So let's go ahead and draw a diagram on the left-hand side. So, they're saying the main curve, right, is y equals x and y equals 1. You want to find the region between those. So, let's go draw the curve first. So, how will we draw it? Let's draw our activity first. Let's make it big. X, y. Okay? And then y equals square root x. Do you know how that looks? Right? Easy guys? That's y equals x to the half. Okay? And I guess we can do the same thing here. Because they say, remember, you're revolving it around the line, y equals 1. Okay. So now, what we need to do is, you've written y equals root x. Now, what you need to do is about the line y equals 1. So simple. Let's draw the line y equals 1 in. So this is, let's say, where y equals 1 is going to be, and that's between x is equal to 1 and 4. So they're saying between the x values of 1 and the x values of 4. Now, let's draw a dotted line. That's the line y equals 1, and about here, right? See, when x is equal to 1, if you sub it in here, root x, 1, the y value is 1. When x is equal to 4, the y value is square root of 4, which is 2. So this top value should be 2. Okay? Now, and they want the area between these two curves, like straight up. And line y equals 2. Right? They want this region here. That's what they want. Let me use a different color to highlight what the region they want. No. That's a bad drawing. Let me redraw it. Let's make it at least appealing to look at. Yeah? And let y equals 2 be somewhere like here. Not really a big change, but only to make the simplification process easier. Y, x. Nice. Y equals x to the half. Easy. Okay. Now, the area that we want to find is this area. Okay? This area that is between these curves. And they're saying it's rotated above the line y equals 1. When you rotate this entire curve above the line y equals 1, that's not what they're doing. What they're doing again, we do not need this extra diagram at all. My bad. I interpreted the question wrong. So that's 1, that's 4. They're saying this is root x. 1, find the region. You want to find the volume of the solid revolving the region of this. This is the region. We just found the region. Good. First part, tick. But they want us to find the volume, and they want us to find the volume about the line y equals 1. Okay? So about this line, y equals 1. So you want to rotate this about this line. So we're rotating it in the x-axis. So you see, we're rotating in the x-axis. So it's going to be a dx man, but they want it to be like this. Something like that. And they also want us to find this volume. Okay? That makes sense? Yeah. Let me rub out this green part here. Why? Because I want to show you something else. Now, think about this. Why did I just draw this line? Think. If you already know this, you can skip this part, but let me explain to you why. See this line, right? When you revolve this line, when you rotate this line about the y, this is how it's going to be. When you rotate it about the x, or the line y equals 1, which is on the x-axis, it's going to be this, right? But then, imagine you rotate this so fast that it becomes a 3D object. See, the more and more you rotate this, right? Try visualizing this in your head. It's going to become a 3D object like this. Yeah? It's going to be like a bullet-shaped 3D object. And bullet-shaped 3D object. And let's say, and the way you find out any of these volumes, right, is by separating this figure into smaller cylinders and then finding the volume of that one. Right? We can find the volume of this cylinder. And what's the volume of any cylinder? The volume of any cylinder is just its height times the cross-sectional area. And that is pi r squared because that's a circle. So pi r squared. And in our case, we want to find out the radius. What is the radius? Then the radius is going to be, take this entire, what's the radius going to be here? For this cylinder, right? What's the radius going to be? What's the r going to be? Well, the r in this case, the r is going to be, take this entire length, right? See fx, let me demonstrate this better. Let me draw the diagram again for you. One. Right, so this is what we want to focus on. So we can erase this bit. Right, this is what we want to focus on. And we just wanted to find the area of this, the volume of this cylinder, because it's just going to be the volume of many cylinders approximated to a smaller figure. Okay? What's the volume of this? Because we know the volume is equal to pi r squared h. Already? Our h, we can let that be delta x, which will then become dx. Okay? Don't need to worry about that. Then let that be delta x. Okay? What's the r going to be? Well, quite simply, the r, let this be delta x for now, and the radius is going to be this entire length of this top curve. See, this is y equals, what is it again? Root x, right? So that's fx. So when you sub in fx, we will get, see, at any point on this number plane, when you sub in a number like x equals 3 into root x, it will give you a y value. So that height there is the y value at a given point. So it's going to be pi, the radius is going to be fx, because fx will give you this height. Fx will give you the height from this point all the way down here, from the x-axis all the way down to the point. Because when you sub in the x, the y value there is that. But we do not want that. We want this area. We don't want all this excess space. So what we can do instead is, see how this, they've given us a line y equals 1. Find the radius of that. If you draw a smaller thing, what's the radius of 1? That's just going to be 1. So it's going to be fx minus 1 squared on h. That's our volume. Okay? And what's our fx? It's going to be root x. So it's going to be root x minus 1 whole squared h. Okay? That is our volume. If you want a more concrete proof, let me explain it here. So we know now since we know that since r is equal to root x minus 1 from the graph, our proof would be, take the limiting sum as this approaches 0. So the limit as, and this is, the height is going to be delta x, for example, right? Remember that, delta x is the height. What's delta x? Small change in x. Small change in x. So limit as delta x approaches 0, that's what we're going to find. Of what? The sum of all the ones from the point, let's say that's A and that's B. That's the region from x equals A to B of this pi root x minus 1 squared delta x. That's a volume, right? We want to approximate this to such a small number so that we can find the absolute area of the volume. And that's going to be, if you don't get this, it doesn't matter, just remember it. Okay? That's going to be the sum of becomes elongated x from A to B. The pi you can take outside, root x minus 1 squared, and the small change in x, right, becomes dx. And that is our volume. Okay? Now, let's use that here. That's the volume. Now what do we do? Well, we want to find the volume. So let's just go ahead and do it. That's just going to be, what's root x minus 1? That's going to be x minus 2 root x plus 1. But we're going to integrate this, right? dx from 1 to 4 pi. And let's integrate it now. So x squared on 2 minus 4 plus 4 on 3. Wait. What is this again? Subarolin. Okay. Subarolin. I'll make the life easier. I'll just write the calculation here. That's how you find it. So not a lot of working out, but then that's, if you understand the radius, which is going to be that f of x minus y squared. And that's why it's a general form, right? So volume when you rotate it about an horizontal line, it's just equals to pi a to b f of x minus a squared dx. That's the general form. understand.